Welcome to our NPTEL lectures on power quality improvement technique. Today we shall discuss about the PWM rectifier. This is one of the entrant of AC to DC conversion. So, we know that we require to rectify it. Once we rectify it for the diode base rectifier or the control rectifier, then we inject also the harmonics. But we shall see that this is the property of the, allow me to change the color of the ink. So, properties of this ideal rectifier. So, it is desired that a rectifier presents a resistive load to the AC power system that leads to one unity power factor operation. Another is that AC line current has the same wave shape as the voltage, since we know that IAC equal to VAC by RE. So, where RE can be said to be the emulated resistance. So, this is something what we want while you convert and you have the same equivalent, though here you got an AC, this is a voltage and this is a current. Depending on the magnitude of the resistance, you just have some kind of scaling. Here you will have this value and this value. So, this has to have some kind of analogy. This is the voltage and this is the current. Now, so we require to establish an since in AC average value is 0. So, we have to talk about the RMS. So, average DC power should be is equal to V square AC RMS by the equivalent resistance or the effective resistance by V control, and the power apparently consumed by RE is actually transferred to the rectifier DC output port. So, thereafter you got a DC voltage. To control the amount of the output power, it must be possible to adjust the value of RE, so that you can transfer the maximum power. So, this can be think of we can this is the AC current and the AC voltage, and this one is equivalent resistance, and ultimately your transferring power is equivalent to VAC square RE, and here in this port it has the transformations, you got AC output as well as you got a DC output and the DC current. So, we require to, this is the output port model of rectifier or AC to DC conversion system. Ideal rectifier is lossless. We assume that switches are lossless and contains no internal energy storage. Hence, the instantaneous input power, the AC power, equal to the instantaneous output power. But there is a problem here, generally it does not match, then it will not be then AC, because if you multiply in phase component of the voltage and current, then what will happen at the 0 crossing, then your instantaneous AC power is 0, and thus you require to have a instantaneous DC power is also 0, and thus what essentially you will get is this, not a pure DC, the ripple DC. Since the instantaneous power is independent of the DC load, so we are not talking about, since you know this is the expression of the power and there we do not talk about the loading of the DC portion. So, we can say that since the instantaneous power is independent of the DC load characteristics, the output port obeys the power source characteristics, and ultimately this power is given by V square AC by RE control, or B instantaneous into I instantaneous equal to P instantaneous, that is given by V square by AC by RE, where RE is a voltage control resistance. So, equations of the ideal rectifier. Now, why you require it? Of course, we have discussed about the 6 pulse 12 pulse converter. There we have seen the problem and we want a ideal rectification, and see that how it can be achieved by the PWM rectifier. So, defining the equations of the ideal rectifier is that IAC equal to VAC by RE control. Similarly, that will be equal to Vt into It equal to Pt, or Pt equal to this instantaneous value. Whereas, when connected with the resistive value, the input and the output RMS voltage and current are related as follows: V RMS by AC RMS equal to under root of R by RE. So, AC RMS by RMS equal to under root by R by RE. This is the expressions. It is something like transformer kind of entities. So, we require to rectify. So, this is the rectifier. We are showing you a single phase model, but this is the effective DC to DC converter, and thus it gives you the isolation for the sensitive load, and also it ensures that voltage and current within the phase. So, it will ultimately, you can see that at this moment it takes the Vg. So, Vg, since with the absence of the capacitor, we will have a profile like this, and similarly Ig also will try to maintain within the range of the value of the Vg, and thus this instantaneous multiplication of it matches, and ultimately here in this side you get a ripple DC, but with the DC to DC converter you get a constant DC. But there is a power factor problem is solved, because since voltage and current are in phase, so there is no displacement power factor and all those other nasty element, and it is also free for the harmonics. So, in that way you can mitigate by using a real rectifier the problem of the power quality arises because of the rectification process. So, that is what we say, the control of the duty cycle of DC to DC converter such that output current is proportional to the input voltage, that is essentially your, as if it sees the resistive load. So, current and this is the voltage at this point, and Ig will follow this voltage, just having the same thing with the less or more magnitude depending on the value of the Re. So, this is your Vg and this will be the Ig. So, this DC to DC converter will force that Ig here will be following the envelope of Vg, and thus in here you do not have any problem in power quality. So, this is the few waveforms. So, this is the input voltage which we have applied, and we want that AC current should be like this Vm by effective resistance, and for this reason I have drawn Vg in previous slide, that this will be the value of the Vg and this will be the value of the Ig just by Re, RE can be more than 1 or less than 1 depending on this magnitude of the IG will vary, but output voltage here will be a DC value and this will be your IDC, that is also constant. So, what you require to do here, we have to maintain this duty cycle that is inverse to the voltage and current, so that it follows this kind of pattern of voltage and current. This will automatically come, you need not have to do anything for the rectification, but DC to DC converter will force this current to be like this, and ultimately capacitor will ensure that your DC voltage after isolated DC to DC converter is this, and for this reason your DC to DC converter will have this kind of modulation index. So, what is modulation index? MDT, it is Vt by Vg, essentially this is constant and this is variable. So, it is quite clear that once you are here, you require to generate this voltage, you require to have a more on time, whereas where you are here to generate this voltage you require a less on time. So, in that way this modulation index itself will be varying to give you this DC voltage, and ultimately you will find that Ig is also following, and thus this reflection will come into the input waveform, and this will be also a sinusoidal waveform. In that way we can eliminate the problem of power factor as well as the THD in case of the in case of this AC to DC conversion. So, thus what we can say, this is the averaged over switching period, IT equal to Vg into IT by Vg, this is the unit template of the current. So, we can rewrite it as Vg T by Vre. Similarly, IT equal to, we can write in terms of the we can multiply this two. So, V square by m Re sin square omega t, and thus we can split. So, this part is DC, that is Vm square 2 Vre 1 minus cos 2 omega t, that will have a double frequency ripple, and average over the AC line period I will be V square m to Vm Re. So, P will be equal to V square m by Re. So, ultimately this is your rectifier portion. Mind it, there will not be any capacitor, capacitor will be at this, and Ig and Vg has to follow that particular envelope which has been shown to you in our previous slide, and this capacitor has to maintain the DC bus voltage, and in that way operation follows. So, the MDT equal to Vt by Vg equal to V by Vm sin omega t, and we will have this kind of modulation index. And thus, these are the few issues to avoid distortion near the line voltage 0 crossing. The converter should be capable to produce producing MDT approaching infinity. So, this is something we require to see that. So, for this reason we will restrict, these are the logical restriction we require to put while designing. This above expression neglects converter dynamics, because there will be a switching losses, there are filters, there will be losses, conduction losses, those are not featured into the these calculations. We can use this DC to DC converter may be isolated as well as non isolated, though I have shown the picture of the isolated. It can be boost, buck boost, choke, SEPIC and other converter with similar conversion ratios, and that can be implemented or it can be used for this purpose. We will see that, and this is the next topic of it in next slide, that we will see that the boost converter exhibit lowest transistor stresses, and that is preferred. For this reason it is most chosen, but it is not that it is not possible to introduce this way of operations, so that your power factor get corrected for buck boost or the Chook converter. So, ultimately this is the overall circuit. I request the student to go through the one data sheet of the Texas Instrument UC3855X, X can be 5556, so on. This is the data sheet for the chip, this controller, that will ensure this power factor correction technique as well as the low THD. So, here operation is same. We require to generate the Vg will be this, and we require to force Ig to be stay into the envelope, just magnitude will change. Ultimately, we will sense this Vg and Ig and get all those calculations done, which has been shown into the previous slide. Then accordingly DC duty cycle of this MOSFETs has been calculated, but please note that MOSFET should have a body diode. So, another issue is that for the higher power rating we require IGBT, and generally as you know that it is a single phase application. So, it can be up to 3 kilowatt. So, this is the way of doing it, because 220 volt in our cases India it is 220 volt and you got a 15 ampere line. So, you multiply straight away you get 3 kilowatt. So, this power factor technique can be extended up to 3 kilowatt, and for this reason for the lower rating we can go for this MOSFETs, and for the more than 2 kilowatt we generally prefer to go for the IGBT. So, DC motor voltage, the peak of the input voltage. The controller varies the duty cycle. So, this is the case. DC output voltage, in this case this one is more than the peak input voltage. Why it does not work? Why you require to a boost phenomena? We require to generate the rectified voltage. Generally what happen, all to get a after rectification you will find that there is a capacitor. So, the current will not flow unless capacitor voltage is crossing. So, this is your rectified voltage, current will flow only in this duration, and for this reason you have a problem of the displacement power factor and the THD comes out. But in this case what happened, you are shorting this switch. So, instantaneously your voltage, this voltage get 0, and accordingly you build up the voltage and you ensure that you are keeping these values within the range of this the simulated value of the Vg and Ig. Thus, the controller varies the duty cycle necessary to make Ig proportional to Vg. Now, so there is a way to achieve it, the variation of the duty cycle in case of the boost rectifier. This topology is called the boost rectifier. So, it is MDT. So, that is V by Vg, V by Vm sin omega t. Since m is greater than 1 in the boost converter, it is required that V is greater than Vm. If the converter operates in CCM, that is in a continuous conduction mode. So, that is what we want, and if the that is also a challenge, but if the load is light, then it does not work. So, then this value MDT will be equal to, in case of the boost converter, that is 1 by 1 minus d is the V 0 by V in is 1 by 1 minus d. So, this has been replaced here, and thus the duty ratio, therefore, it will follow is that dt equal to 1 minus Vg by V, but it is for only continuous conduction mode and control is easy. And accordingly, we require to design the rectifier and also this inductor, so that it remains in a continuous conduction mode. So, this is the way we can calculate it. So, the inductor ripple is Ig equal to Vg dt into Ts by L. This is the current ripple that you will allow inside the inductor. So, you know that this there is a boost topology, thus current will go up, go up, go up, come down. So, the ripple what you have allowed, assuming that it is a critical conduction mode. So, it will always touch 0, and for that assumption we have this current ripple, and for the low frequency or this is called the average model, the component of the inductor waveform is, that is Vg is definitely it is given by Vg by Re, that is the average value of I, what the straight line I have drawn, this the average Vag. So, converter operates in CCM when Ig of Ts is greater than del Igt, and that equal to dt, and that is the limitations. So, that value is 2L Re into Ts, where Ts is the switching inverse of the switching frequency, or you can take F in numerator. So, substituting this value for the condition to be in this converter into the continuous conduction mode will be Re equal to 12 by Ts 1 minus Vg of t by V, and that is for the continuous conduction mode. So, this is the condition for the continuous conduction mode, or the if it is equal, then it is a boundary condition. So, this is we are now going to discuss realizations of a near ideal rectifier. So, Re is 12 by Ts, what we got 1 minus Vg by V for the CCM mode. Note that Vg of t varies with time between 0 and Vm. Hence, these equations may be satisfied at some point of the AC line. So, AC line is basically you got a V and I. So, you can draw the value of the effective value of this Re. So, the converter operates in the CCM provided that this logic RE equivalent, that is a load essentially, ultimately you should be knowing that load, and so ultimately it is 5 kilowatt or 3 kilowatt, and what is the current rating of it. From there you can calculate the RE. So, this RE value should be less than that 2L by Ts. So, value of the inductor has a strong relation with the switching frequency. So, ultimately if you want that it is 20 ohm, and let us consider that it should be 2 millihenry. So, you can calculate this should be the switching frequency minimum required to operate, whether which device will be suitable, MOSFET or IGBT. And on the other hand, the converter always operates in DCM mode, that is that is discontinuous conduction mode, when RD, if RD is more than this, and thus what happened for this RD. Between these limits, the converter operates in DCM Vg near 0 and in the CCM when Vg approaches to Vm. So, it will have a transitions from continuous conduction mode to the discontinuous conduction mode, but thus that transition does not occur, because that whatever the expressions of the duty cycle you write for this buck boost, choke, SEPIC, all are valid for the continuous conduction mode. The moment you are in a discontinuous conduction mode, analysis become complicated. So, let us think about the realization of the nearly ideal rectifier with the power factor correction. A plot of the input current Ig versus the input voltage Vg for various cycle dt in continuous conduction mode, the boost converter equilibrium is Vgt by Vm equal to 1 minus dt. The input characteristics in DCM is found by the average DCM model that is shown in this figure, and this is the Vg, and ultimately this resistance has been modeled, that is 2 L d square by dt, and this is the power available to you, that is Pt, that is V minus Vg, and effectively since this the voltage is available to you, the control voltage, and this is your DCM. Thus, in DCM Rd from the previous is same as emulated by Rd equal to Vg by Ig. So, now simplify this DCM in expression to obtain 2 L Vt Ig 1 minus Vg by V equal to dt squared dt Vg by dt by V, and thus DCM mode of the boundary in terms of Vg and Ig, it will be 2 L Vts Igt equal to or greater than Vg by V 1 minus Vg by V. This will be the total expressions in case of the discontinuous conduction mode. So, this is the overall pictures to analyze the boost rectifier. So, ultimately this is the circle within, after this you can see that discontinuous conduction mode starts, and this is your load line what I was trying to draw there. So, that is the Igt, that is Vg by Re you can see that if duty cycle is 0, so no questions. If duty cycle is 0.2, this is the boundary for the continuous conduction and the discontinuous mode. In this mode, it is a discontinuous mode, and where all those condition exists. Till this mode, you are in a discontinuous conduction mode, and here this is your MGT, that is, that value will cross over. Similarly, if your duty cycle is 0.4, your crossover will occur faster, and ultimately you can, since the value, it is light load, because this is a value of RE. So, you have this portion of it. It is the challenge is that it maintaining this ideal characteristics of this rectifier, the light load. So, from there you will take the continuous mode of conduction, and when duty cycle is 0.6, you can take the almost follow the load line, and this is the above load line. So, you will reach to the this continuous to conduction mode to the conduction mode faster. So, ultimately in DCM expression is pretty simple for the boost converter. So, so it will be Vg by V 1 minus dt, but in case of the discontinuous conduction mode, expressions is quite complex. So, it will be 2L by Vts Gt 1 minus Vg by V, that equal to d square Vg by V, and once it comes into the domain of the continuous conduction mode, then 2L by Vts into Vg, that is Vg by V 1 minus Vg by V. This is the way it should operate. Thank you for your attention. I will continue my discussions on this rectification technique for single phase as well as 3 phase in our next class.